Impedance matching is a complex topic with multiple possible implementations ranging from discrete components to transmission lines, the choice of which is usually done based on frequency and bandwidth requirements. Today, I want to look at a distributed element method which can be implemented as a wideband matching circuit, the stepped impedance transmission line transformer. So if you're curious, then keep watching. To highlight the workings of such a component, today I will later be testing some implementations that I got from today's sponsor, JLC PCB. To better understand the stepped impedance transformer, we need to start by remembering the quarter wavelength transformer. So when analyzing the structure, an impedance transformer in which two resistive impedances are connected with a piece of transmission line that is a quarter wavelength long and has an impedance equal to the square root of the product of the end impedances, or if it makes for a better understanding, the impedance as seen from one end is the square root of the square of the line impedance divided by the end impedance. We can quickly confirm this in the circuit simulator. So in this case, I'm using 1 nanosecond long transmission lines for 3 different load impedances. And well, the calculated transformer should provide matching at around 250 MHz based on the transmission line length. So if we run the simulation and we check the signal on the signal source side, so the 40 ohm transformer, the 25 ohm, and the 10 ohm, we can see that indeed all of the transformers are working. They are providing impedance matching at the 250 MHz point, where we are getting the -6 dB attenuation and 0 degrees of phase shift. However, the interesting observation to be made is that while this is a narrowband matching technique, the exact bandwidth that is being obtained is different in our 3 test cases, and it depends on the ratio of the matched impedances. The closer the two impedances are, the wider the bandwidth. So just with our small experiment, we can see that the widest bandwidth is obtained for the 40 MHz transformation. So here we have the flattest response, and the narrowest bandwidth is obtained for the 10 ohm load, where we have the narrowest response. Now, although creating an impedance transformer like this works just fine, no one is forcing you to go between the two extreme impedances in one single step. So the core idea of the stepped impedance transformer is to use multiple steps, so multiple impedance transformations, and create a gradual impedance transition. So just to confirm this idea, I took our initial 50 to 10 ohm impedance transformer, and I will be comparing it to a similar structure, but this time built from 3 different transmission lines. So with this thing, we are going from one impedance to the other, but in multiple intermediate steps. So first we go from 50 to 35, then from 35 to 20, and finally from 20 to 10 ohms. So based on these intermediate impedances, I ended up calculating the necessary transmission line impedances for each step. So if we run the simulation like this, and we again look on the signal source side, so first to our single transmission line, and then to the one constructed in 3 steps, we can see that indeed we are getting a different response. So the center frequency of the matching network is still the same. We are getting our -6 dB point with 0 degrees of phase shift at 250 MHz, but the frequency range in which we are getting very close values to this is much wider for our 3-step transformer compared to our single-step transformer. So in other words, adding more steps has helped us increase the bandwidth a bit. So the approach does seem to work, but I just chose the intermediate impedances randomly. Surely there must be a proper way to do this, right? Now, I highly recommend this article from the Microwaves 101 website, since it explains the various response types, and you also have more detailed linked articles describing the mathematics behind each structure. So here you will find a very thorough description of the topic, but to keep things simple, there are 3 main types of responses that are commonly used when designing a stepped impedance transformer: a maximally flat, a equal ripple, and an exponential. For the same number of sections, the maximally flat has the flattest and least steep of the responses. the equal ripple is, well, the most ripply, but also has the steepest response, and while the exponential is a sort of a compromise in between the two. It has a bit of ripple, but it's also steeper than the maximally flat. To highlight these, I calculated a set of examples that transform 50 ohms into 10 ohms using 4 pieces of transmission line. Now, the exact line impedances in each case are different, and thus our response should be different. So if we quickly simulate, and we have a look, so again looking on the signal source side, we have our maximally flat response. So here the load is matched over a wide frequency range with minimal impedance deviations. So this roughly goes between 180 and around 320 megahertz. Then we have the equal ripple response, which is providing matching over a wider range, but with quite some significant ripple. And well, finally, we have our exponential response, which has a more reduced, but also uneven ripple. Finally, we can have a look also on the load side. So we have our maximally flat, equal ripple, and the exponential responses. So more or less a similar story to what we were seeing before. Now, in all fairness, I did not calculate the section impedances by hand, but rather I used this worksheet, which is also present on the Microwaves website in the download section. So with this tool, you define the exact end impedances, the number of sections that you want to use, and well, the rest of the fields relate to the display. And well, this tool can be used to calculate the necessary impedances for your transformer for up to 8 sections. And you also have the 3 different response types. So the maximally flat, the equal ripple, and the exponential. And the graph will give you an indication of how the response should look like. So using this will be much quicker than implementing things in the simulator. It's a much faster way to get a visual representation. The last thing to point out regarding this topic is that even if you use an infinite number of sections, you will still never get an infinite amount of bandwidth. To better understand this, let's go back to how a piece of transmission line works when it's connected to different end impedances. So the transmission line will provide an impedance transformation based on this rather complex formula. So this is quite useful to compensate for various complex loads. However, there are 2 very specific cases for this equation. First, when the length is exactly a quarter wavelength and the load is resistive, the formula simplifies into the classic impedance transformation. This is what we're using in our quarter wavelength impedance transformer. And the other extreme occurs when the length is a half wavelength. Here, there is no impedance transformation at all. So the stepped impedance transformer will always have frequencies where it just doesn't work, when the individual sections are exactly half wavelength long transmission lines. Now, this point was also visible in our simulations. There was always a frequency where no impedance transformation was occurring. So, no matter how many sections you're using, this behavior will always appear. So, stepped impedance transformers are a wide band matching technique, but you will still be limited in the maximum continuous bandwidth that you can actually obtain. Now, the transformer looks really nice in the simulator, and the mathematics seem legit. But how well does this actually work in practice? So for this, I created a test board with 3 different test traces. The idea here was to create an impedance matching circuit that goes from 50 ohms on the SMA connector side to 25 ohms on the other side. So this load is implemented with a couple 50 ohm resistors in parallel. The intention of this setup was to measure from the signal source side and see when the observed impedance is 50 ohms. The exact difference between the 3 traces being that the first one is a simple quarter wavelength transformer. It has the same impedance throughout its entire length, and the second and third one are stepped impedance transformers with 2 and 3 sections where the exponential response type was used to calculate the necessary impedances. Now, the exact boards that I used are 4 layers, and I got them from today's sponsor, JLC PCB. Ordering a board is as simple as pulling your Gerber file onto their website, and the tool will automatically import it and determine the exact size, layer count, and calculate your approximate price. So 4 and even higher layer count boards are quite affordable. Specifically for design like a stepped impedance transformer or any other structure where tight impedance control is really needed, one of the things to keep in mind is that one of the high spec options that you need to select is impedance control. So once you activate this, you need to select the exact stackup that you need. So let's say we need this one, and the website will calculate if there's any changes in your price. And you can also check out the impedance calculator just to verify the exact dimensions that your traces need to have the specific impedance that you want. So try JLC PCB today using one of the links below. Now, after getting the boards, and well, assembling them, and finally connecting them to a measurement equipment and starting to test, first of all of the circuits are working. We do see an ever-increasing bandwidth the more sections are added. So this experiment does highlight the benefit of making multiple section stepped impedance transformers, but it also highlights two things that are very easy to overlook. Or well, I was not paying enough attention and well, missed them. So the first thing, if we overlap all of our measurements, we can see that they are not really centered around the same center frequency. Rather, the first peak is kept, and then from there on, the traces are overlapped. The reason for this being that the complete structures have the same physical length, but different section lengths. To get the same center frequencies, all of the sections should have had the same electrical length. They all should have been a quarter wavelength at the frequency of interest. The way things are, all of the free structures that I have built have different center frequencies. And well, this does highlight an interesting problem though. The more sections that you add, the larger the matching transformer becomes. So even though you might want a 10-section very wideband device, it might just be a bit too large to actually be practical. The other thing to highlight can be better observed in the Qt Studio simulator. So one of the important features of this software is that it doesn't just have ideal transmission lines, but also you can build structures that are based on specific realistic substrates. So for the simulation, I considered an FR4 board that has a 4.5 relative permittivity and about an 0.02 loss tangent, and well, the typical 1 ounce copper thickness of around 35 micrometers. So for this experiment, I created 3 different impedance transformers, an ideal quarter wavelength transformer, a realistic one, and a 3-section transformer. All of these designs are created to go from 50 ohms to 75. And well, if we look on the response on the input side, so on the signal source side, we can see that all of them are providing impedance matching at the same frequency. So we see our -6 dB point. However, if we look on the output side, all 3 of our transformers are giving different peak response values. So the largest output amplitude, the one in red, is coming out of our ideal transformer, and the smallest one in pink is coming from our 3-stepped transformer. In fact, if you look at it, the 3-stepped implementation seems worse than not having any sort of matching at all. So in other words, the more sections that you're adding, the more losses the real device will end up having. So this is a very important consideration when you're actually going for this sort of a device. The second important aspect of the practical board that I overlooked was the exact lengths when using different trace impedances. So I simply split the entire length into equal sections. However, if we check the exact electrical length of equal physical length structures, we will observe that there are subtle differences. So now I'm back in the Qt simulator, and if we open the line calculator tool present under tools, and here we can select one of the available transmission line types, and fill in the material properties, frequency of interest, and so on, one of the things that we'll notice is if we change the width of our trace, So right now with 1 millimeter, it's 48 ohms. If we go to 2 millimeters, it's 33. If we go to thinner ones, it's 65, so it's higher. So obviously the trace thickness does give us a different trace impedance. This shouldn't really be a surprise. However, if we also check the induced phase shift, so this is a different way of observing electrical length. So at 0.5 millimeters, we have 298 degrees. At 2 millimeters, we have 318 degrees. So if you always want to get the same electrical length, so for example, 90 degrees for a quarter wavelength long transmission line, you will need to slightly change the physical dimension for each desired impedance. So that is why in my 3-section transformer, each section has a different length. The differences are not huge. Here it's only a few millimeters, but it's still an important aspect to keep in mind to get the best results. Now, another fun fact about this line calculator is that it will also calculate the trace losses. And these are separated into conductor losses, dielectric losses, and radiation loss. But anyway, once you're happy with a specific geometry, you can simply select Copy Component to Clipboard, and in the schematic, paste it directly. So this is a very easy way to copy information between the tool and the simulation. Now, just to confirm that you can actually trust the simulator and the predictions that it makes, I created our free stepped impedance transformer equivalents. So for this I used the dimensions of the physical traces, as well as a description of the substrate based on the manufacturer's designs. Now, as specific simulation, I used an S-parameter type of simulation, since this gives you the results in the form of, well, S-parameters. And these are quite easy to process in a similar fashion to what the VNA is doing. So here I put in the syntax to display the impedance value as seen by the ports. So now, if we look at the actual measurement results and compare the simulation to the measurement, so here we have the 3-stepped impedance transformer, then we have our 2-stepped impedance transformer, and finally the single-step quarter wavelength transformer. We can say that it's not really a perfect one-to-one match. There seems to be some sort of glitch with my measurement, and the exact values are a bit smaller. However, all practical boards will have some amount of tolerances after all, so other than these small differences, we can say that the results are good enough to be able to be trusted. So performing a simulation first, before creating the actual board, should provide quite a bit of insight and help you achieve your goals a bit more easily. Finally, a special case of the stepped impedance transformer to consider today appears in microwave applications, where the individual quarter wavelength sections become relatively short, comparable in fact to the width of the trace. At this point, adding, say, more than 10 sections is no longer that big of an issue. So here, you will find that the transition from one impedance to another is sometimes implemented as a smooth rather than a step structure. So this can be visible in multiple points on this specific design. Now, coming back to the Microwaves website, another set of important articles are the ones describing tapers, and specifically the Klopfenstein taper. So these articles describe the structure and its performance in a lot of detail, and specifically for the Klopfenstein taper, you also have a calculation sheet available to download. So this can be used to calculate the exact dimensions needed when transitioning from one impedance to another. So long story short, the taper can be designed as a stepped transformer with a large number of steps, but the actual taper is implemented as a smooth transition from one impedance to another, but with the shape dependent on the individual impedances through which you have to go to get the correct impedance transition. Multiple specific shapes are common practice, and the general consensus regarding these two types of implementations is that both structures have more or less the same impedance transformation behavior, but the smooth one is much easier to implement in practice, since it's not very feasible to have all of these right angles on a small PCB structure. In the end, the stepped impedance transformer presents a wide bandwidth impedance matching technique, which is especially useful in high-frequency applications where constructing the various non-standard impedance values is possible and practical. In a sense, you can say that it's a more complex version of the single quarter wavelength transformer, but the usage of it, specifically the number of steps that are implemented, should always keep in mind the exact losses that will be appearing. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.